Alright, we're going to continue with our rational functions, and the last part of our section of this unit is we're going to look at how they relate to the graphs. So we've been adding, subtracting, solving equations, all those kind of things, but we really haven't looked at the graph of rational functions. So today what we're going to do is we're going to start with just some basic ones, which are the reciprocals, and then we'll look at the more complicated ones in our next lesson. So if you look at this diagram, y equals x is our red line here. So that's our red diagonal straight line, linear line. And if we graph 1 over x, we actually get this blue curve. So the first thing you notice when you see this is they're quite strange looking. We get these weird kind of graphs when we do fraction kind of graphs. So they often look confusing because of the fractions and non-permissibles and things like that. But if we break them down and look at each piece, they're not so bad. So let's start with just a linear line, y equals x plus 3. And we're going to do the reciprocal of that, which would make it 1 over x plus 3. So it's a rational function just by doing 1 over. So the first thing we want to do is let's actually go through some of the coordinates of each of these, and then we'll see how they relate to the graph and kind of look at comparisons and things like that from there. So let's start. I've made a data table here from -5 to 3. So let's just look at the values for each. So if we plug -5 into the linear graph, we'd have -5 plus 3, which gives you -2. Plug in -4. -4 plus 3 gives us -1. -3 plus 3 is 0, and so on. We just keep going. You can see we basically just go up by 1 each time. Okay, so that's pretty simple. And to plot those points, we would just get our straight line. So at -5, we're at -2. So these squares are going up by half. So -5, -2 is there. -4 and 1 is there. 3 and 0. -2 and 1. 0 and 3. 1 and 4. And the other ones are off the grid. But you can see those are our... Sorry, I screwed up that one. -1 and 2 is there. 0 and 3. And there we go. So there's all of our coordinates of this data table other than the last few. But we can see it does make a straight line if we connect the dots. So now let's do the same thing for the 1 over. So you can see if we plug a -5 in, we'd get 1 over -2, or -1/2. If we plug in a -4, we'd have 1 over -1, which is still going to be -1. Let me actually write those out the way I just said it. So we'd have 1 over -2, which would be -1/2. For the 4, we'd have 1 over -1, which is -1. For 3, we'd have 1 over 0, which is undefined. We can't divide by 0. And if we continue with these, you can see -2 is 1, so we'd have 1 over 1, which is 1. I'm running out of room here, but we'll continue. For -1, we'd end up getting -1/2. For 0, we'd have positive 1/2. I messed up on that, because with 0 in there, or -1 in there, we'd have 1 over 2. Let's change that. So we'd have 1/2. For 0, we'd have 1/3. For 1, we'd have 1/4, 1/5, 1/6, and so on. Okay, so if we actually graph those now, let's kind of look at that. So 5 is at -1/2. So where we started on the first one, we were at -2. When we do -1/2 now, that shifts down to there. So 1 divided by -2 becomes -1/2. The 4, -4, 1, you can see is in the exact same location as the original. So that coordinate didn't change. Okay, the 3, 0, you can see is now undefined. So how we're going to actually draw that as undefined is we're going to represent that as a vertical dotted line. And we'll get more to that in a minute. And we continue, we can see at -2, 1, we have the exact same coordinate again. And at -1, we got 1/2, so you can see where that one is. At 0, we got 1/3. At 1, we got 1/4. And at 2, we were at 1/5, and so on. So there's all of our coordinates. So you can see we've got most of them. They're following the graph. We didn't get any near the -3 line, so we could actually make more up if we want. We could put in, let's suppose we wanted to try to do -3.1. So on your calculator, if you type in 1 over -3.1 plus 3, you actually get an answer like negative 10. So at negative 3.1, just beside that dotted line, we're way down here at negative 10, so we're quite a ways down. And we could do the same thing. We could look at something like, say, 2.9. That would give us 1 over 2.9 plus 3. Sorry, negative 2.9. So negative 2.9 would give us something like 10 again. So when we're right close to the dotted line on the positive side, we end up getting really big. So we could do that with more and more points, but you can see we actually get those blue curves. So there's a couple of key things we want to recognize with these two graphs. We get two sets of coordinates in this case that are exactly the same, the negative 4, negative 1, and the negative 2, positive 1. And the other one that's an important thing to be aware of is what's happening at that 0 location. So when we had our x-intercept in the original at negative 3, 0, that became undefined in the new graph. That was our vertical line, right? So we put a vertical line in, dotted line at that x-intercept on the original. So those are sort of the key things you want to be aware of with the graph. If we look at that, we see that that x-intercept of negative 3 on the original becomes our non-permissible, and we get our dotted line. You can see our original, we'd have a domain would be any real number. In this case, it's still any real number, except we can't have anything at that negative 3. And y is any real number. Our range then ends up being the same thing. We can't have a y of 0. So we kind of look at our coordinate that we had, negative 3, 0, that matches our domain and range for our new graph. So first thing we're going to talk about is what that dotted line was. We're going to call that an asymptote line. So it's a new word, and it's basically a line that the graph will never cross. And the vertical asymptotes are going to occur wherever our non-permissible values are. And those non-permissibles that we just saw in the last graph is where our x-intercept was on the original. And those horizontal asymptotes actually occur as well. And in most cases, what we're going to look at, our horizontal asymptote is along the x-axis. So if we go back to the last graph, we could have drawn a dotted line along the x-axis as well. So you can see we kind of get this cross, and you can see our curves just go in each corner of those two areas. Okay, so let's look at a new graph. So this is some other line. I have no idea what the equation is, and it really doesn't matter, because what we want to do is highlight where is, on the original graph, where is x equal to 0. That's going to become our asymptote. Or sorry, not where x equal to 0, where y is equal to 0. So where y equal to 0, that's going to be at negative 3. So that's our first key point. So where y is equal to 0, that's our asymptote, so that's going to be when x is negative 3. So at negative 3, we can draw our vertical asymptote. We know our horizontal asymptote is going to be along the x-axis, so we can sketch that one in right away too. And the only other key points are going to be where y is equal to 1 and where y is equal to negative 1. Those are going to be our other key points. So you can see here we've got those 2 points don't change. That's our location of the same thing on both graphs. So we'll get to those in a sec, but let's just kind of review the asymptotes. So wherever our original x-axis is, or our non-permissible, that's going to be our asymptote line. Those other 2 points where they're going to be 1 and negative 1, those are going to be our invariant points. An invariant point is a point that doesn't change when we go from one graph to the next. So both of these end up being the exact same point, because we get 1 divided by 1, which is still 1, or 1 divided by negative 1, which is still negative 1. So because we're divided by 1, and when you get 1s for these, it will not change. So if we go back to that same graph again, our asymptote line was where y was equal to 0, and that occurred when x was negative 2. And we had our horizontal asymptote line, which was right along the x-axis. We want to figure out where y is equal to 1 and where y is equal to negative 1, and that's going to be our invariant point. So in this case, where y is equal to 1, you can see we're at negative 2. So oops, I messed up. That was negative 3 was our asymptote line. So negative 2 and 1 is our first invariant point, and you can see our other one ends up being at negative 4 and negative 1. Okay, so that's it. Once you know the invariant points, you know the asymptote lines. After that, we just draw our curves in like that. We can see it approaches both sides. If you're ever not sure, you can always put the graph on your calculator if you get the equation and go from there. The rest of the coordinates end up just being reciprocals. So every other coordinate is just going to be 1 over. So what we see here is if we pick any other coordinate, so let's look at this one up here. We had a 3 for our y coordinate. That now changes down to a third. If we pick some other coordinate along here, let's look at this one down here. It's at -3. It becomes negative a third. Another coordinate here is at -2. It becomes -1/2. And so on. So we just basically continue. Basically, we can plot every point on this graph just by doing 1 over. So it doesn't really matter what the coordinate is. We're basically always just doing 1 over in order to get the new location. So you can see in this case our y-intercept was at 3, and now our y-intercept becomes 1/3. So a number that's really, really big, 1 divided by a really big number, ends up being really small. So that's why it's approaching infinity down here. And if we get something that's really, really small or close to that asymptote line, 1 divided by a really small number is going to be really big. So that's why those lines end up approaching infinity. So let's do the exact same thing now, but actually doing it from an equation. So I want you to graph 1 over x minus 4, and let's figure out what the asymptote lines, invariant points are, and domain and range. So I'll just kind of sketch it here. So our graph looks something like that. If we were to graph our original, x minus 4 would end up being a diagonal line that looks something like that. So that's our original. So now let's calculate all of our new things. So our asymptote, remember, will be when y equals 0. So we just got to look at our equation. When is x minus 4 going to equal 0? Well, that's going to occur when x equals 4. And we know from our graph that it's our x-intercept on the original becomes our asymptote line on the new one. Okay, so there's our asymptote line. Let's figure out our invariants. So our invariant points occur when y equals 1 and when y equals -1. So let's solve that. So we'd have x minus 4 equal to 1. We solve that, we get 5. And the other one would be x minus 4 equal to -1. And we solve that, we get, add 4, we would get 3. So that means that the coordinate 5, 1 is one invariant point. So 5, 1 would be about there. And the other one would be 3, -1. So 3, -1 is about there. We also know our other asymptote line is our x-axis. We can kind of sketch that in, and we're good to go. So we know that our curve has to go between these two asymptote lines, and it's got to go through that invariant point, and the same thing on the top quadrant. And that's it. So you can see our domain and range for our original, remember, was xer for both and yer. That was for our original green linear line. So now you can see our xer, our domain for the new one will be any real number except we don't have a coordinate at the asymptote line. So we just write that as x can't be 4. And our range, same thing. Range can be any real number except we don't cross the 0 line. That's where our horizontal asymptote is. So we just say y can't be 0. Okay, makes no difference if we have a more complicated thing on the bottom, same thing. So we'd go 2x minus 3, figure out where that's equal to 0. We get 3/2. So that means on our new graph we would have a dotted line at 1.5. So that's our asymptote line. Then make it equal to 1. So that'll be 2x equals 4, x equals 2. So that means we have a 2, 1 is our first invariant point. Make it equal to -1. So that case we get 2x equals 2. So that means we get 1, -1 is our other invariant point. We know our other dotted line would be right along the x-axis, and that's good enough. We can draw our graph now. We just basically draw our curves in each quadrant again. Make sure we go through our invariant point, and we're done. So domain again would be any real number except for that asymptote line, so 3/2. And our range would be any real number again except for our horizontal asymptote, which is 0. So before we stop, we'll just look at one more type of question where we get a quadratic. So if I was to graph x squared minus 9, that gives us our red quadratic shape. So using the same logic, we should have, because we have 2 x-intercepts this time, we should actually get 2 asymptote lines. So you can see this first intercept is at -3. So we actually get our vertical asymptote line at -3. And then we also have another one at +3. So we get another vertical line there. We still have an asymptote line at the x-axis, so that goes across like that. So that hasn't changed. So our asymptotes are at 3 and -3. And our invariant points will still be at the 1s, but now you can see we get 2 graphs across at y equals 1, and we have 2 locations across at y equals -1. So in this case, we would just estimate the coordinates. We'd see that when x is negative, that's a little bit past 3, so let's just estimate it at about 3.2. That one's at +1. If we go a little bit less than 3, so approximately 2.8, that gives us -1. And when we do the other side, those are at a little bit past 3, so let's say 3.2 gives us +1, and 2.8 would give us the -1. And you could use your calculator if you wanted to get these exact decimals, but estimating in this case is good enough. So you can see everything works exactly the same. The only other thing that you got to be careful of with quadratics is when it comes to the domain and range. So we can see that we have our asymptote line, so our domain again would be any real number except for 3 and -3, right? We don't want to have those asymptote lines. And normally our range we would say anything but 0. But the trick is this graph actually, the top part goes above 0, so that part's still good. Y has to be greater than 0. But if you look at our bottom part, our original vertex on this graph was at -9. So that point actually, when you do the reciprocal, would be -1/9. So we actually have the bottom part of the graph only peaking out at -1/9. It doesn't go any higher. So we actually put that in as part of our range. So our range ends up being less than or equal to -1/9. And that's it for that one. So let's try one more. So this time we'll just sketch it out and solve it mathematically. So let's do our asymptote once again. So that'll be where our equation is equal to 0. So if we solve that equation, we would get x squared equals 3. If we square root both sides, we get plus or minus root 3. So if we were to sketch this out, root 3 as a decimal is 1.4 or whatever. So root 3 will be somewhere between 1 and 2. Let's just estimate it something like that. So those would be our 2 asymptote lines. Okay, let's do our invariant points. So that'll be where minus x squared plus 3 is equal to 1, and minus x squared plus 3 is equal to -1. So if we solve those, we get minus x squared equals -2. And if we square root both sides, we would get plus or minus root 2. And if we do the same thing with the other one, we get -4, square root both sides. In this case, we get plus or minus 2. So that means we get 2 and -1 is one coordinate, -2 and -1 is the other. And then over here we have root 2 and 1 and negative root 2 and 1. So 2, -1 is down here, -2, -1 would be somewhere down there. And then our positive ones are at root 2, which is like 1.4 or something like that. So we'd have there and approximately there. So this one, because we know it was -x squared, our graph originally was upside down. So in this case, our new graph actually ends up being upside down as well compared to the last one. So we would have our bottom parts doing our same kind of curves like we had before. So that hasn't changed. Our top part, if we were to actually sketch our original graph, it would have a vertex at 3, right? The original would be an upside down U-shape peaking at 3. So that invariant, our inverse point is going to be at -1, or positive 1/3, which would be somewhat like that. So then our top part is going to do a graph like that. So our domain again will be anything except for plus or minus root 3. And our range would be y is, in this case it's less than 0 and greater than or equal to 1/3. And that's it. So hopefully you understand that. We'll be doing more examples in class, so you'll have lots of chances to see what these look like from the graph and from the equation. You should have a good idea of what these graphs look like. Remember, you can always do this on your calculator to help you find what the graph looks like, to help you find where those invariant points are or asymptote lines, all those types of things.